Okay, now it looks better. Okay, so today I'm going to talk about some of my latest research where we were thinking about, well, how to characterize sample complexity in online reinforcement learning. And I would like to start the talk with an observation. So as Deb was saying, I did my PhD in control engineering and then later moved on and worked a lot on optimization and machine learning and related areas. And when I transitioned, what I found interesting is that in machine learning, people tend to have extremely strong opinions. So, for example, with the introduction of AlexNet, there's been the claim that computer vision has been solved, right? If you talk to roboticists, for example, Ken Goldberg at Berkeley, he will say, well, it's actually not so simple, right? So even if you have stereo cameras, it might still be hard to get robots to really understand and interact in a smooth way with the environment. Then now with the advent of ChatGPT, the claim is around that natural language processing has been solved. But then, of course, there's again more cautious opinions, such as a house cat is smarter than the best AI, right? And the question, you can go on and on, right? And the question is really what is now happening, right? And why are there these strong beliefs and these strong opinions, right? And I think one of the reasons is that we still struggle to understand really the fundamentals. And I think a lot of this is based on essentially exploration or extrapolation from an observational setting where we just observe a process and try to make predictions about how it's going to evolve, right? To the setting where we actually intervene. Right? And so this poses fundamental questions about whether is there a difference between just observing something, right, and interacting. And you can pose this question in numerous different ways. And to me, and also I guess to many of you, this is a question fundamentally about passive versus active, right? And in RL, we try to think about active problems. We try to interact and we try to steer with a system and dynamics, right? And so to have maybe a more concise mathematical question, we could ask ourselves, well, is there a difference in sample complexity between supervised learning and reinforcement learning, right? And I think also a question that is very relevant is what are actually the easy and what are the hard reinforcement learning problems, right? And with this talk, I'm trying to share my thoughts and some of the ideas that are related to these questions. Okay, and so if you have questions, you can interrupt me at any time, and I'll try to answer. Okay, so the first point I would like to make, so what are easy problems, what are hard problems, right? And we're here at the workshop Intersections RL and Control. So if there's no learning, then I would like to emphasize that the picture has been solved quite well, right? So in the field of control, there's a beautiful theory that tells us precisely what is a difficult control problem, what is an easy control problem. And we can get results that characterize for a given set of dynamics what is the corresponding performance that we can hope to achieve, right? And an example, a very illustrative example is this one, where you could, for example, balance an inverted pendulum, right? So a stick, right? And as you make the stick smaller, the unstable pole gets way faster, right? And at some point, the stick is too small so that I can balance it. I can no longer balance it anymore, right? And it's not about computational resources of me and about not having enough experience or not having enough data, right? It's just that my hand, so my actuation and my vision system is too slow, right? And so no matter how much data, how much compute you throw at it, there's certainly certain problems that you cannot solve, right? Simply because of hardware limitations. And so for those of you who don't know about this, I think it's something that control theory has developed very well. And here's, for example, a reference, right? And in my own research, this pops up a lot, right? So here's a bird, and I find it really fascinating how this bird can hover in place, right? And so what this bird does, there's rising air, and it adapts it's the shape of its wings, right, to just harness the airflow from the environment and just hover in place. And together with my PhD student, we've been developing a robot that can do the same, right? So here's our wind tunnel, just built by off-the-shelf components. And then here on top is our flying robot. And so this is the video that shows how it works. So similar to the bird, right? The robot just changes its shape, and that's all it has to control itself. And it can harvest essentially the energy from the environment. And so compared to a quad, for example, you can reduce energy consumption in this wind tunnel with its specific experiments by 50 to 80%. And we can track attitude. We can also track position. And of course, it's very turbulent. So it's quite a challenging control problem. And we can also land, as shown in this video. Now, why am I bringing this up? Well, when building such a system, there's a question on how do you design it, right? How do you ensure that this is actually going to work? And initially, we thought about multiple designs. One is shown here, right? So you could also arrange these flaps in these directions, right? And by essentially rotating these flaps, you could try to control all the different degrees of freedom, right? Now, it turns out that if you look at the dynamics, there's essentially one tilt axis, right? So there's a sort of concave shape and a convex shape. Along one tilt, it's convex. Along the other, it's concave. And along the concave shape, you have an unstable, you have essentially unstable open loop dynamics. And the rate of this instability is so fast that, again, no matter how much data and how much compute you throw at it, you're never going to be able to handle, to stabilize this, this design, right? And it turns out that you have to modify, or you have to think about more elaborate designs. So we added these kinks. And so as a result, you have a convex-convex shape, a global convex-convex shape, and that makes it work, right? And again, this sort of understanding of what are easy problems, what are hard problems, what are problems that we can solve, what are those that we cannot solve is crucial. And here's another example that I really like. So this is a balancing robot, right? And the special thing about this balancing robot is that it's actuated by a single reaction wheel. So you can't really see it in the slide. I apologize for that, but there's a single reaction wheel that's rigidly mounted to the robot, right? And you might, so for those of you who have had some experience in dynamics and in mechanics, you will notice that there's here two unstable tilt axes, right? One along this direction and one in this direction. And it's kind of remarkable that you can actually stabilize both with only one input, with a single reaction wheel, right? And the way this works is as follows. So it turns out that so here's the two tilt axes, by a careful design, right, by introducing this elongated structure, you have a lot of inertia along one direction, very little inertia along the other direction. And the controllability analysis tells you that there's, in this case, actually a closed form expression that gives you that the inertia along one axis divided by the inertia along the other axis is 1 over 1 plus square root 2, right? So by choosing the ratio of inertia in this way, you can actually maximize performance, and you can make sure that this robot can actually be balanced, right? And you shouldn't be fooled by this nice-looking video, right? So it took us about three years plus to get this working, right? This is an extremely challenging task. With only one reaction wheel, you control these two unstable tilt axes, but in fact, you also have to account for structural vibrations in this beam. And so in total, it's about 12 degrees of freedom, most of which are unstable or marginally stable that you have to control with one reaction wheel. So it's really extremely underactuated. Okay, so in the absence of learning, right? we understand what are difficult, what are easy problems, and control theory had essentially contributed a lot to this question. Now, what I would like to talk is, well, what happens if we add learning to the picture, right? Can we still think about using these control theoretic quantities and incorporate them into our sample complexity bounds that we're going to get for characterizing the behavior when there's learning, right? So in this case, so previously we had a model of the system. We assumed the dynamics are known, right? What's the best performance that can achieve? Right? That was the question. Now here the question is, I'm interacting with a system that I don't know, right? I need to figure out the dynamics at the same time that I want to optimize performance, right? Okay, and again, I think an important question is what are easy, hard problems? And so the formalism or the setup that we looked at can be described as follows. So we're assuming that there's a finite set of models, right? And these models are captured by this capital F. So they're just enumerated F1 to Fm. M is the number of models. And each of these models describes stochastic dynamics, right? So here we have stochastic dynamics associated to each model. And so there's process noise here. And for simplicity, we say it's Gaussian. And I'm really interested in continuous state action systems, right? So I here is the model, and X and U are state actions, right? But these are continuous, right? I'm interested in continuous problems. Okay, and what makes this this formalism interesting is that it's an attempt to go beyond the linear setting, right? So in principle, but we're going to see, of course, there's some limitations, but in principle, these models can be nonlinear, right? And they can also incorporate constraints by different choices of these FIs. Right? It's continuous state actions, and I think the fact that you have a finite set of models, we're also going to discuss this later on. But from an engineering perspective, it's actually quite a natural assumption because it gives you a way to incorporate prior knowledge, right? You can set up your candidate models by essentially incorporating the engineering knowledge that you might have about the problem at hand, right? Now, what's the goal? And here we're putting a reinforcement learning perspective on the problem, right? So we're interested in maximizing or minimizing, in this case, performance. And so performance is characterized by this loss function evaluated at states and actions. And because we have stochastic dynamics and our policy will also be stochastic, we take an expectation. Right? And of course, we have some regularity assumptions. So we're assuming that the loss is smooth and that these are Lipschitz continuous, for instance. Okay, and now the question is, what is this quantity here, right? So what we characterize here, or what I wrote down here, is policy regret. And so the question is, what is the benchmark here? What is this gamma? And from a control theory perspective, this is a nonlinear H2 gain, right? But you could think of this as really optimizing. You could compare against the performance that you could have achieved had you known the best steady state policy. So we're looking at steady state policies, no time varying policies that minimize the long-term cost, right? This long-term average. Okay, so what's an example? I think an example that I would find interesting is to see whether this approach can be applied for supply chain management. Right? And in particular, these different, so the state could represent the inventories along your supply chain. These different FIs could actually be a way to incorporate different predictive models about future supply demands, about potential delays that you have along your supply chain, and so on and so forth. Right? Okay, and yeah, let me know if you have any questions at this point. So here's the algorithm that we're going to analyze, right? And the algorithm follows a paradigm. So again, from a control perspective, it introduces a type of separation principle that separates between model identification and feedback controller design. From a reinforcement learning perspective, it's a mix of, it incorporates some Thompson sampling aspects or posterior sampling aspects, where you try to find a good model. Right? And so let's go step by steps. So here's how it looks like. So for each of these candidate models, right, you would compute, and you can do that offline, right? So you'd compute the corresponding feedback policy. And of course, in many ways, this is computationally intractable, right? But this is not the complexity I want to measure in here, right? Now for linear systems, so for linear dynamical systems, this amounts just to solve an LQR problem. So you can, given your linear dynamics, you can just compute these very quickly, right? So we start with these set of policies, and these are certainty equivalent policies, right? So they operate under the belief that, so mu1 operates under the belief that model 1 is correct, and so on, right? Okay, then what do we do for adaptation? So what do we do in the online setting? Well, we're gonna incorporate some excitation, right? And it turns out that we want to make sure that we excite enough, right? So, and the critical quantity that we're going to look at is whether we can distinguish between two different models. And so we need to introduce this two-loop procedure, right, where you wait for a certain number of steps, and this certain number of steps m, that guarantees that you have enough excitation so that you can tell two models apart. Right? So that's going to be the critical assumption. And here, what I'm doing is, or we're adding here, kind of naive exploration, right? And of course, in many practical problems, this is not the way you want to go, right? But you will see the analysis essentially works, or still works, as long as you can guarantee this notion of persistency of excitation, being able to distinguish between two models over these m steps, and as long as there's a bounded second moment for your excitation, right? Yes. So F is the true dynamics. Yes, yes, yes. So here we're assuming that the true dynamics are part of the model class, right? But there's also a version of this where you don't need to do that, but then things get a bit more complicated, right? But that's a very good question, right? For simplicity, we're looking at the case here where F belongs to the true, or the true dynamics correspond to one element in your model class. Yeah, yeah, exactly. Okay, and in a linear case, this constant CE, so these can actually be computed explicitly, and this constant CE relates to the controllability of the system you have. Okay, so let's continue. Then what do? You look at how each model performed over the last iterations, right? And then you sample a model from this exponential distribution. And from a Bayesian perspective, what it does, it's a notion of posterior sampling. The difference is that you introduce this parameter eta, so you're a bit careful here. So if eta is really, really large, then this would be maximum a posteriori. If eta is close to 1, this is posterior sampling. And we'll need to see that we need to choose eta in a reasonable range, small enough. And then finally, you apply excitation, and the corresponding model or the corresponding policy that belongs to the selected model. Right? Okay, and the neat thing is that there's a beautiful or a very simple argument that you can make. I'm going to walk you through that allows you to conclude policy regret guarantees out of this algorithm. And the main assumption that we're operating is really this persistency of excitation, the fact that we can distinguish two models. Right? And in particular, the bound that we get is a constant times log of the horizon, log of the number of options, and then a constant term. And we can work out these constants explicitly, right? So, but I didn't show the expressions here to simplify the understanding. And again, the benchmark here can be taken as the policy belonging to the true dynamics, so the best steady state, right? And in particular, I started the talk by asking the question, well, is there a difference in sample complexity between supervised and reinforcement learning, right? Turns out that what we did here was we reduced the problem to an estimation problem, essentially, right? And so what we get is that despite the dynamics and despite the fact that we have to learn about the dynamics in an online way, right? We essentially reduce the problem to a supervised learning problem, and we get similar rates, right? So in particular, we also get this log m divided by n as you have it in supervised learning. Okay, so a few more points. So here's the previous bound for the setting of finite models. Now we can also apply covering and packing arguments. So in this case, in particular, packing arguments, where if our set of models is just a bounded set in a normed vector space, we can just pack this space, right? And epsilon is going to be our packing width, and then m of epsilon is going to be our packing number. And for a given set of functions, you can then try to optimize this quantity, right, by choosing an optimal packing width, right? And so in that sense, you can also generalize the result to a broader class of functions. You can apply a similar argument to actually deal with a parametric case, right? So instead of having these finite sets of models, we can say these models are parametrized by a parameter theta, say, and then the corresponding policy regret guarantee is going to be square root n times the dimension of your parameter space, right? And you can use any neural architecture you want in principle for parametrizing your models, including also transformer architectures. And one thing that's interesting here is that by following this packing approach and guaranteeing persistence of excitation, you actually get no regret learning for a large set of systems, right? And here, in the special case of linear dynamics, you also directly get a result that characterizes policy regret in this case. For linear dynamics, essentially P is just the number of parameters that you have, so the number of parameters in the A and the B matrix. Right. Okay, and of course, this is a very fundamental problem, and so it's been studied over many years. The contributions that we make here is the fact that we kind of use multiplicative weights, hedge type of analysis for understanding the convergence to the best model, and then tying it to kind of a more control theoretic point of view that is based on dissipation inequalities, right? So that's the combination here. And of course, there's been numerous previous works characterizing sample complexity based on the Luder dimensions or linear Markov decision processes, right? Then there's also been work on the online linear quadratic regulator, right? But for these proof techniques, it's sometimes difficult to extend this to nonlinear dynamics. And then there's online optimal control where people are more following these approaches, but putting in structural assumptions such as contraction on the dynamics and so on and so forth, right? And then there's also the field of multi-model adaptive control, which is reminiscent to what I just showed. Okay. But with that, I want to show you now the argument, right? How can we conclude this result? And I can actually sketch the proof argument in 2 slides. Here's the first step. So the first step will be used to guarantee that the probability of us making a mistake, so not selecting the best model, decays rapidly, right? And why is this true? Well, the intuition is that we can look at the prediction error, right? And in this case, we have squared prediction error because our process noise was Gaussian, right? And so from a maximum likelihood perspective, this is the prediction error you should look at. And you can decompose this into different parts, right? One part here is essentially the signal, so the difference between the prediction of the true dynamics and model I, right? And then there's this linear term and this quadratic term that depend on the process noise. So if you compare now the one-step prediction error accumulated over different steps between model I and the model corresponding to the true dynamics, what you see is you're going to have two terms. One is this term here, and one is this term linear in the process noise. And it turns out that by the assumptions on the process noise, this gives rise to a martingale difference sequence. And so as a result, there's concentration, right? So as a result, you know that this is going to concentrate around 0. And we're going to use here this notion of persistence of excitation to ensure that this term is going to be bounded below. Right? That's the argument. So more precisely, we can therefore look at the moment generating function, take via concentration. Of course, we have to work to make this equalities approximate sign here precise, right? But intuitively speaking, we can take the expected value to the exponent, and then by this assumption on persistence of excitation, we get the noise of our exploration that we put in here, right? And on the lower bound, we get essentially that the probability of choosing model I is then bounded by this term. Okay, so that's the first step. Second step works as follows, right? So in the second step, we can actually use the value function or Lyapunov function corresponding to the best model, right? And we're going to analyze how this evolves. And the way you can analyze this is you can distinguish a favorable and a non-favorable case, right? So in the non-favorable case, you make a mistake, and so your IK is not equal to the true model or the true dynamics, right? And then the favorable case is where you made the correct selection. Now, the good thing is that this part here decays quickly enough. So we have a decay of 1 over k squared, right? And that's going to save us here. And here in the favorable case, things are going to be fine, right? And now in this unfavorable case, what we can argue is that based on smoothness assumptions and Lipschitz continuity, we can argue that this value function is not going to blow up in finite time, right? We will have an exponential decrease in value, but not in finite time. And so we can derive an inequality of this type, right? And combine it then with this fast decay. And for the favorable case, we just have a Bellman type of inequality, or from a control perspective, a dissipation inequality. Right? And we can put both together, and then we get a sort of telescoping sum, and that then leads to the result. Right? Okay. So I hope I gave you a sketch of the proof idea. Right? Okay. And so with that, we're concluding this part, right? So what I showed you is a separation principle that allows you to do optimal control design given understanding or given that your model is true, right? And you can separate this from the estimation part, so estimating your models, right? And it turns out that when you put both together, even though you might have nonlinear dynamics, right, you can still get policy regret if these assumptions are, policy regret guarantees if these assumptions are satisfied. Right. Okay. So in the remaining part of the talk, I still have 15 minutes, I think. I want to discuss kind of one of the fundamental paradigms that I see a lot in reinforcement learning, right? And it's the idea that we optimize over feedback policies, right? So also in the earlier part of the talk, right, we always constructed feedback policies. But it turns out that computing feedback policies can be really, really hard. And in particular, there's work that, for example, highlights that in deep reinforcement learning, your results might actually also even depend on your random seed, right? So it just tells you that computing policies can be really, really hard in general, right? Now, if we think about how nature essentially incorporates control algorithms, then usually what you have a combination of feed forward and feedback, right? You have a notion of planning and anticipation, and then a notion of reaction, right? And I think this can be illustrated with like an everyday experience, right? If you drive a car and you want to stop at a stop sign, you make a plan for what's ahead, right? But then you update your plan and you take feedback actions based on how things evolve, right? And so there's really both feed forward and feedback that are important. And yeah, and so in this work, in the work that I'm going to show you, we took this to an extreme. So this is joint work with Onno Eberhard, a student in my group, and Claire Bernard, who's a group leader in Tübingen. And yeah, and we took this to an extreme. So we looked at the open loop control only, right? So here the setting is you want to just figure out what's a good sequence of actions. But again, you don't know the dynamics. So you have to constantly interact with the system over multiple episodes, figure out what's a good sequence of actions, right? And it turns out that in many of the reinforcement learning benchmarks, there's very little noise, right? There's very little noise in the simulations. And so deploying feed-forward actions actually works really well, right? So for example, here in this inverted pendulum, there's essentially no noise, so we can just make it swing up, right? And similarly, in these Mujoko examples, right, we can actually solve these quite well just by computing a sequence of feed-forward actions. But the holy grail is to combine both, right? Ultimately, we want to have reaction and we want to have a planning and anticipation part. And so this is some recent work also by people in my group. So Hao Ma is a PhD student in my group, and then Melanie is a collaborator from ETH and so on. And so what we did was to think about this 2-degree of freedom control structure. So from a control theoretic point of view, you would draw the following diagram. You would sample a reference trajectory, right? In reinforcement learning, this would be a sequence of goal states, right? And so my notation is such that this yref describes an entire sequence, right? Then I'm taking this sequence, I'm putting it to a neural architecture, for example, a convet, and out comes a sequence of inputs that a good plan of how I want to control the system. And that's what's going to be applied. And then here, there's also a feedback component, right? And of course, the question is, how do you train the system? So how do you update feed forward weights and feedback weights so that you get the desired behavior? And one approach that works extremely well in practice is to simply use a model, right? So an approximate model of the system you have, right? And then you can just evaluate and compute approximate gradients. So the model will give you approximate gradients of the system part, and then backpropagation will give you the appropriate gradients for feed-forward feedback controllers, right? And so you can easily compute approximate sensitivities that tell you how your output is going to change as a function of your network parameters. You can also do finite differences. And so for finite differences, what you do is you inject noise, right? And then you can evaluate this quality by taking finite differences. Right? And this works really well. We can actually deploy this and get robots to learn in an online manner, right? And so we did this robot that over many years, and we still have our basis. at the MPI. And the special thing about this robot is that it's driven by pneumatic artificial muscles, right? That makes it really cool and really challenging. But we also apply this to larger scale systems, such as so this is not going to work. Well, right? So we can get tracking error by performing online experiments. So we can get down. Driving activities is actually really challenging, and it requires a lot of human expertise to do well, right? And so if we can automate this process, it's a good thing. And here's another example. So this is collaboration with EPFL, where we drive the soft robot. So there's this elephant trunk that's essentially driven by a cable pulling mechanism, right? And again, we can deploy the approach I showed you and learn how to track different trajectories very well. And the last example before the end of my talk I want to show you is I think an example that's actually really relevant as well. And this is again collaboration with Brad Nelson at ETH, and Yazan is one of my PhD students. Now we're thinking about these magnetic actuation systems, right? And the premise or the idea is to use these magnetic navigation systems to do actually minimal invasive surgeries, right? So for example, you can design catheters, right? And that have a magnetic tip. And then by essentially using this magnetic actuation, you can then drive or navigate the catheter inside the patient's body, right? That's the idea. And so in this visualization, you see how this could look like. So by controlling the magnetic field, you can then orient and steer your catheter, right? And another exciting application is targeted drug delivery. So where you can actually then deliver drugs at dedicated points in your body. But Yazan and I, we're control engineers, right? And so we take the system to the next level, and we're interested in moving a bit away from the ultimate or immediate medical applications. So what we do is we play around with feedback, right? And while the standard approach for driving the system has been more or less in an open loop manner, right? So you put on a large magnetic field, and then the catheter will simply orient along this magnetic field. What we can do instead is we can constantly measure how our robot is oriented, and then just do very small corrections to that. So applying small levels of torque, right? And this leads to a new actuation principle, right? So the traditional actuation principle is to generate large fields, then have the robot align, right? But what we can do or what we're investigating is how to use torques and forces to just make very, very small corrections. And this actually leads to a save in current from about 10 amps or so down to a few milliamps, right? And that's extremely important because the current is what's determining the heat that you're going to produce. And so in these more medically relevant applications, there's a lot of engineering design that goes into cooling. And so by adapting a clever actuation strategy, we can reduce the amount of cooling, right? Now, in this video, you saw a playful example of some of the experiments we're doing. So we're balancing this inverted pendulum, right? And so the bottom part is actuated, the top part is not actuated. And maybe the next video shows this also nicely. So we can, again, the bottom part is actuated. There's the permanent magnets here, and then we balance the top pendulum, right? And so this is really a task where feedback is crucial, right? You constantly need to adapt and make corrections. And in particular, this learning-based strategy, right, of feed-forward feedback controller is important. And we can, for example, improve tracking by using some learning components, right? So we can reduce steady-state errors in a very effective way. So repeatable errors in a very effective way. We're also going in direction multitask, right? So we can actually control two pentalots, two different locations. And here's the last thing before I'm going to stop. We can also just do levitation. So this is a video from last week where we're actually able to, again, there's a permanent magnet here, and we can now control this device very precisely in the entire workspace. So this requires controlling the field in the entire workspace very precisely. And so with that, I'm at the end of my talk, and I'm happy. I would like to thank the PhD students in my group for the excellent work they're doing, and I would like to thank you for your attention, and I'm happy to take your questions. Thank you.
Thanks, Michael, for the nice talk. So any question?
There's a question up there.
Hi, thanks for the nice talk and the impressive demonstrations. In your proof, there was a condition that the cost-to-go function has to be smooth, right?
Right.
Do you have some? For me, it's very hard to have an intuition for how restrictive that is. Is that like likely in practice, and would you be robust to that?
Yeah. So what I can say is that this works perfectly if you have linear systems. Right. If you have linear systems, then the cost to go is a quadratic, and then everything works, right? And you would expect that as you deviate slightly from this, you would still have this sort of well-behaved behavior, right? So your analysis will still go through. But then with systems that where you might have different equilibria and so on, or maybe also non-smooth dynamics where you might have impacts and so on, it might be challenging, right? So that's all I can say. Yeah.
Right. Yeah. Thank you.
Yeah. You can also speak up, I think. Or.
Yeah. So I had a question about the separation assumption that you had in those theoretical results. Maybe can you say a few more words about that and how that appears in the guarantee that you have shown?
Right. So the separation principle is a classical thing in control theory, right? And in particular, it's about controlling systems where you don't have full state information, right? And so traditionally, you would do optimal control design based on knowledge about the state, and then couple that with an optimal estimator design, right? And it turns out that for linear systems with quadratic costs, you can put both together, and you get the optimal feedback controller, right? And that's very powerful, and it's used over and over again because it allows you to reduce the complex problem into two simpler ones, right? Now, here, the separation comes about because it's not about estimating the state, but in a way, it's estimating your model out of the set of candidates, right? So, but what you do is you do a type of posterior sampling, right? And so the posterior is really capturing distribution over different models, which is related to the state estimation. And then you apply the corresponding certainty equivalent controllers, right? And what was surprising to me is if you do it in a precise or in a good way, then it can work, and then it can lead to these policy regret bounds. Yeah.
So there, kind of my more precise question was that okay, I'm willing to buy this assumption if you have like a finite number of models that no matter what I do, if I get enough data, I'm going to be able to rule out all the incorrect ones and just zoom into the correct one. It's going to be all correct. But then you also showed results for classes with bounded covering numbers, assumptions, and this is where I start to have some well, I'm not saying like doubts, but some questions about like how does this argument exactly work for such continuous function classes as well? Because for finite, I can see that you're eventually going to separate out the
right.
Model, right?
So the idea is to just follow the same paradigm, right? So there's different notions, so you have to read the details of the paper. There's different notions, right? Different problem settings. So one is where you just say your class of functions is a bounded set, in a norm vector space, and there you would just discretize, and then you're again in a finite model setting, and in principle you can then rule out different options. Now, if you're in this parameterized version, again, what you try to separate is parameters that work well for the true dynamics, right? And then you have kind of like an epsilon ball around your parameters, and then you try to rule out the rest. But now, of course, this assumes continuity, right? So you're assuming that within your range of parameters, your dynamics are similar, right? And so you can effectively rule them out, right? So of course, yeah, for certain problems, this might be challenging. Yeah. Thanks.
But I guess like in the end, this is still like a structural assumption that you place on the model class,
right?
Which may or may not be weaker or stronger than the other things that we have listed, like bounded eluder dimension, linear MDP stuff.
Right. So I'm currently reading about this and figuring out. Yeah, it's hard to relate all of these concepts because also some of these were for discrete MDPs, right? And then I'm trying to approach this more from a continuous state action space perspective, but yeah, I'm working on this and trying to find like the relations. I think yeah, we can also discuss offline.
Thank you.
I can see for the linear systems, like you can do this, you add a noise to the parameters, you are happy. But like in other cases, how
would you explore?
Yeah,
right?
That.
Yeah. But I mean, again, I think this interesting work that could be done on top. Yeah, I think if you want to approach the analysis through this paradigm of separating identification and control, then the natural thing would be to figure out an excitation strategy that allows you to distinguish between models, right? And of course, if you have your dictionary of models, you could try to solve this computationally, right? You could try to, for your state that you're at, planning like a certain number of steps ahead, you could try to optimize your excitation so that you get a lot of information to distinguish between different models, right? That's one way I could. It's not clear whether it's doable. Yeah. Of course. Yeah.
So going further in the whole persistent excitation in the modeling space, because the context that you are exploring is control, the notions of imperfect learning, I mean, what if you can't introduce the kind of excitation that you need in order to do this identification, control, separation, et cetera? That it gets into some what kinds of issues do you face?
But yeah. No, what I can say is that what you saw in the analysis is essentially I'm trying to think about the best case scenario where you can get this excitation, right? And then you indeed converge to the best policy in hindsight. Now, if you don't have excitation, it turns out that your estimation error has like a monotonically decreasing property. So suddenly, if persistence of excitation is not holding anymore, you won't be able to distinguish between different models, right? But you're then just, you're not going to reach optimality, but as long as you have enough information to get a reasonable estimate, it's going to be fine. And you can also apply kind of the argument to derive that your value function is going to be bounded. So you also have boundedness results if suddenly persistence of excitation fails, right? Yeah. Yes, in the estimation error. Yeah.
Persistence, like you don't require it even as, let's say, linear MDP, where I understand better. You don't require it always roughly log the number of times. Basically, each episode once, if you inject, that's enough for in the excitation.
Right. So yes, you decrease your excitation over time. Yeah. Yeah. That's also, and that's a key aspect, right? You need to trade off precisely the amount of injection you put in to like get to, compared to your performance. Yeah.
So, any other question? Okay, or I have. So, I was wondering really about that Pontryagin paper about RL. So we are so used to with the Bellman stuff. So what it gives us extra, because I know from my control classes, like this is very interesting, clean, elegant formulation, but what it brings extra to RL, if you can share.
Well, I just felt that a lot of the empirical RL evaluation in simulation is based on really low noise environments. And essentially the point what we wanted to do is to show, you can solve these problems in just a feed-forward manner, right? But now the maybe more serious take is that I think there's opportunities for combining 2 degrees of freedom. In control, we call these 2 degrees of freedom control architectures, right? Where you combine a feed-forward part and a feedback part, right? And the feedback part is for guaranteeing, disturbance rejection. So in the feed-forward part, right, that's for guaranteeing good tracking behavior. So these are usually orthogonal objectives, and so you kind of can therefore design feed-forward feedback controller to kind of navigate this design space. Yeah, and I think that's a perspective that RL could maybe benefit from. But to be fair, in RL, people actually do this, right? You do kind of some stochastic rollouts, right? And then you try to optimize over these rollouts, and then you have maybe a terminal set or a terminal function evaluation that then characterizes the long-term behavior. So of course, there's also some work. But I think it's an important problem and an important aspect. And if we can, maybe incentivize some of the community to think more about this, it's maybe something interesting. Yeah.
The first is when you introduce uncertainty on top of feed-forward and feedback, then to do adaptation and control at the same time becomes either impossible or very challenging. Because it's not easy to learn feed-forward components. So zeros, even in a linear system, you have zeros that are unknown.
Yeah. It can be difficult. Yeah.
See, because classical control methods
cannot. Okay.
But I think like some practical important stuff, like trying to do similar architecture, but in theory, I think nothing.
No, yeah. Because it's an inverse problem, and inverse problems with zeros are very difficult to solve.
Okay. Thank you for the talk again.